Welcome to the Cryptic talk. First, a little warning. This is not to talk about Bitcoin or other cryptocurrencies. If that's the only thing you're interested in, you will be disappointed. So what are we going to talk about? We're going to talk about cryptography, the art of hiding secrets. So we will show you how it can easily be used in Scala with the Cryptic library. But who are we? Well, I'm Martin Zachrison. But instead of me talking about myself, let's ask AI. And we get this. And you don't need to read that because you can ask your own AI.
Yes, hello, welcome. My name is Odd Möller, and we asked AI the same question here, but it was really much. So I'll just skip that. So let's start. So we're going to speak a little bit about secrets. So to start with, what are secrets? Well, there's any data that's deemed sensitive, right? And what can we say more about them? Well, we have to keep them from being exposed. So how do we keep them? And what if we need to forget the secrets? How do we handle that? Well, one way of tackling these problems is let's encrypt them. So let's start. And keeping secrets, there are basically two different approaches you can use when you're encrypting your data. You can either encrypt on the level of a table or a file, or even an entire database or file system. And this can be called the top-down approach. Using this approach, it likely leads to having a few keys, each used to encrypt a wide set of data. So you're using few keys for a wide set of data. Or you can encode only the sensitive parts of your data. This can be called the bottom-up approach. With this approach, you can have many keys, but each key is only used for a very narrow set of data. And this has some practical consequences we'll look into later. So when you want to forget a secret, how do you do that? Why do we need to forget secrets? Well, we have something called GDPR in the EU, and we need to follow that. It requires us to be able to forget if a user wants to or something like that. And backups can be problematic. How do we delete the user from an already backed up data set? That's not easy. But with a top-down approach, many users might share the same key. So it's not as easy as the bottom-up approach, where you can throw away the key for the specific user. And that means that data is as good as, it's erased basically because you can't access it anymore. You don't have the ability to decrypt it. So why should you use Cryptic for this? Well, the Java cryptology APIs, they're naturally very Java-centric. So we created Cryptic to provide a bottom-up approach, provided in a Scala-friendly way. So you can write code like this with it. Here you have a person, and the email is sensitive, so we put it in the encrypted class or wrapper. And you can use operations on your encrypted values. In this case, we're mapping the email to the domain. It's still encrypted, but you see the types here. So we get back another encrypted thing, but now it's a string, the domain part of the email. And the basic usage is quite easy. Encryption is easy. You just call something, in this case secret, encrypted, and you get back an encrypted value. Decryption is just as easy. On the encrypted value, you call the decrypted method, and you get back a try with a failure if you can't decrypt it or the value it contained. You can also do operations, of course, as we saw. You can transform, say you have a secret you want to transform. You call map on it, and you transform it with, in this case, to uppercase here. You get back another encrypted value, which you can call map on again, or something else, as we'll see. In this case, it does some other transformations here. The operations are staged, so nothing happens. So these two parts doesn't require any decryption to occur. All the operations are run once you decrypt the final encrypted value, and you get back your decrypted value here, right? So that's the thing. But there's more operations. It's not only map. The usual operations are also available, as you'll see here. So yeah, you can use them all, and they're all staged. So they will not run immediately. They will run once you do the decrypt at the end, and it's only the decrypted part that needs any keys or anything else, as we'll see. This allows you to keep all keys and other handling of sensitive information in a separate place in your code. So you don't need to have the decrypt part everywhere. You can also place it in a special node in your cluster, so you don't need to even distribute the keys. You can have them really secure and only use them in that node in the cluster. So, but let's get into the details. We'll look into something called codec. So the codec is used to transform a value of any type here to a plain text, and the decode is the opposite. You have a plain text and you get back potentially a value or a failure. By default, we provide codecs for the built-in primitive types and some other types here, and also option, as long as the value in the value type inside has a codec. But you can also, we have some integrations, and you can make your own. In this case, we have for uPickle, and it's really easy to use. You just import the uPickle codec. And we have something called chill. It's the same strategy, and also FST. And these two, they're not so common in the Scala world, maybe, but they're quite common in Java, because they're like serialization libraries, and they can serialize any type. So they're not based on having all the types. It's more reflection-based, but still, it's possible to use them, or you can make your own. Now that we know about codecs, let's have a look at how to encrypt the value. And for this, we have any type having a codec will also have an encrypted extension method. So this will, if you have a codec for your type, then you will have encrypted available on that type, as long as you have something called encrypt here. As long as that's a given, then you can call this method, right? And you can also provide one version here with a manifest. We'll look into that a little bit later. So as long as you have a codec, you can call these methods. The extension, so this is the call, how it looks then, as we've seen. So the extension method provides for a simple and convenient API for the end user. They only have to see this part, right? This is all imported. So the decrypted method, that's on any encrypted value always has a decrypted method that uses this decrypt thing here. And we'll see what that is. And you get back your try. And the use site is really simple. You just call decrypted, and you get a success in this case with secret. The encrypt is really just a function. Encrypt is really just a function from plain text to ciphertext. Plain text holds the unencrypted data along with a manifest, but the manifest can be empty, so you don't need to provide this, but yeah, you have some bytes there. Ciphertext holds the encrypted bytes, so after encryption, you get back a ciphertext. And the manifest, why is that useful? Well, it's important to encrypt bytes. The encrypted bytes should not contain any structure or anything else that is known about the thing you're encrypting, right? Because that could be used to ease, if you want to break that. Anything you know about the thing inside, you can use that while breaking. So instead of putting it inside the secret, we put it in the manifest. So any non-secret metadata that you want to put alongside the secret, that should go into the manifest. And this is in line with the bottom-up approach of only encrypting the sensitive data, not like the whole package of other data as well, because that could be known. And then back to, and it's not encrypted, that's important. Don't put any secrets inside the manifest, that's not correct. So back to decrypt. The decrypt type is the inverse of encrypt. So it goes from the ciphertext to plain text, and yeah, it could fail, so it's a try. And implementing a crypto is the next thing. How do you implement your own crypto, or integrate, rather? You should integrate. Yes, sorry?
Can I ask, it seems to me that you're not using any kind of salt to randomize the encrypted.
Yeah, we'll come to that. Yeah,
You can,
Okay, the question was, it seems to me that you're not using a salt, and if two people have the same password, you would see the same encrypted.
if you go back to the, go back. These are just function. Sorry. These are just functions. You don't see any details here at all. It's just one function from plain text to cipher and from cipher to plain text. Salt and all that stuff will be in the functions if you choose to have it. You will see later.
Would the ciphertext not have to store the salt? In the type?
Yeah,
We'll look into it.
We'll come to
Okay.
that.
Yeah, good question. Thank you. Yeah, so implementing a crypto, you need to provide encrypt and decrypt, right? That's the thing you need to do. So let's look at the reverse crypto. So here is the implementation of the encrypt. Yeah, it reverses the bytes, so that's nice. And the decrypt, yeah, it basically does the same thing, but on the ciphertext instead. And that's all that's really needed to be able to use this crypto. So a usage of this will be, yeah, you have the secret here and you see the bytes for the plain text secret here. And then you use, yes, I want to encrypt that. I get back something, and it's impossible to know what this is. But once you do decrypted, yeah, you get it back, right? So the use, this is like the user code, but this is what you have to do to implement your crypto. But to make things a little bit more interesting and a little bit more real-like, let's look at a crypto requiring a parameter in some kind, or some input data. So we have the Caesar cipher, and it's a little bit more advanced because it needs like an offset. I think you all know what the Caesar crypto is, but it uses an offset as the key, and then the encrypt function just moves the bytes by that offset. And the decrypt function, yeah, it puts back, takes away the offset, and then you get the plain text back, right? So that's quite easy to implement, and this is the implementation here. And if you want to use this Caesar, then you, of course, you have to, it's almost identical to reverse. The only difference here that this requires a given key. So this key was defined by Caesar, the crypto, and you have to have one of those, otherwise you won't be able to call this encrypted. And you also need it, of course, when you decrypt stuff. Yeah, and if you note, you see that this one offsets the bytes here. So that's the. And in this case, we might want to use. We want to look at the way of using the manifest to store metadata for a crypto. And that's by extending our Caesar crypto with support for multiple keys. So you can have many keys with different offsets. So we define a key map holding the offsets from a key ID. In this case, it's just an int, but still. You have a key ID and you have the offset for that key. And this key map, that's what needed, right? So you can provide all those keys inside here. And we also do a little key ID here on the manifest, which is just a byte array, but still, so you can convert, and we use this to convert it in a stable way. And the encrypt function in this case, here we look into the manifest, convert it to a key ID from the plain text, and get the key ID, and then we get that offset. We use that offset to move the bytes, and then we create our ciphertext with the plain text manifest and also the bytes. So this part is the encrypted part, and this one will be so it's part of the ciphertext, but it's not encrypted, the manifest part. So ciphertext here, it has a special, if you noticed in the earlier ones, there are two, we send in two byte arrays down here. And that uses this method on ciphertext. The apply method accepts any number of arrays, right? At least you have to have one, but you can have many. And they're all joined into one byte array. That's the put into ciphertext. So if we're using this, we can see then that the first 4 bytes of this one is the length of the first array containing the key ID. So that's in this case. See, there's 2 arrays here, and then there's an array of size 4 that contains the 100. This is the key we used here. So we used the 100 key, so we need to store that in the manifest. And then this one is that the cipher, the encoded bytes, the encrypted bytes are 6 long, and these are the encrypted bytes, right? So this is all this, that's put into ciphertext. And if we instead use the 200 key, you see it's the same structure here, but this part is now encrypted with a 2-step instead of just a 1-step for the 100 key. Yeah. And how do we decrypt using this manifest way? Well, we only have to give the key map. If we have the same key map for this Caesar crypto, when calling decrypted, there's no need to give any key ID or anything, because that's stored in the encrypted bytes, right? Or along with the encrypted bytes, rather. So we can decrypt just having the correct key map. And the implementation for that is this. So using the key map here, we see that, okay, we get out the manifest, so we split up the ciphertext, manifest, and the bytes. Yeah, we use the, convert it to a key ID, get the offset used, and then we can decrypt this then, and return the plain text. But yeah, so that was like a quick tour of how you might think doing these cryptos. But of course, friendly warning here, the reverse crypto is not secure, neither is the Caesar cipher. So yeah, they're only toy examples, so you should never use them for real. But to speak about some of the real cryptos you can use, and you should use, I'll let Martin speak here.
Okay, thank you. Are there any questions so far? Yes? Yeah?
Do keys has to be provided in the hash map, or can they be remotely fetched from external key store on the fly?
If you look at, the Cryptic library only wants an encrypt function and decrypt function. Keys are not really part of it. But as we saw in the Caesar cipher, we defined the encrypt function with a using key. But that's just for the Caesar cipher. You can do other things for using, and you will see that. So it's you can have the key. You can have the key in a hardware secure module. That's fine. Or as long as you provide an encrypt and decrypt function. Yes. So okay. So let's talk about. Oh, sorry.
It seems to me that the array in the stored ciphertext is not delimited when you concatenate, for example, the metadata. Yeah. So what kind of safety is there when you're kind of reading that back? It seems to me that in the source code, you need to have exactly the same size manifest that you've stored. Yeah. And if it's missed, if you miss it, the offset by 1, the size, then...
Yeah. Okay. When we do this join, we use run-lang coding, if you saw. So it's... And then... When you define the encrypt method, you decide how you create the ciphertext, and then you should also define the decrypt method. So they go in a pair. So since the encrypt method is responsible for putting the stuff into the ciphertext, and that knowledge should be used by the one that uses the decrypt method. So it's They go in pair. Run-lang encoded. Okay, back to cipher types. There are 2. They're either symmetrical or asymmetrical. And what's the difference between them? Well, the symmetric encryption uses the same key for encryption and decryption. It's fast and efficient, but they have a key distribution problem. How do you securely share a key with the other party? That's a problem, because if you want to send secrets and then you have a secret first that you need to send, that's a key distribution problem. To solve that, you can use an asymmetric crypto, and it solves the problems with the key sharing by having a private public key pair, where the public key anyone can use, and the private key you should keep private. The public key is used for encrypting, and the private key used for decrypting. There is a drawback or a limitation with asymmetric cryptics, and that's that they can only handle a limited data, like a few hundred bytes. And to solve this problem, you can use a hybrid scheme. So you start by generating a symmetric key at random. Then you encrypt the payload using that symmetric key and the symmetric crypto that can handle large data. And then finally, you encrypt that symmetric key with a public key, because the key is not that large. And this way you can encrypt large amounts of data efficiently. Okay, let's look at the provided cryptos apart from Caesar and reverse in Cryptic. So we support AIS and RSA, one symmetric and one asymmetric. They're all part of Java. We also support elliptic curve. It's asymmetric, but it has a hybrid mode. And the elliptic curve adds a dependency on bouncy castle. The last crypto, RSA AIS, will show how you can convert a symmetric crypto to, in this case, RSA, to a hybrid crypto using AIS. Now let's talk a little bit more in detail. So AIS, or Advanced Encryption Standard. It's an industry standard. It's fast. It uses small keys. 256 bits is considered secure today. You don't know about next week or when you get the quantum thingies. It can handle large data, and it's secure if you set it up correctly. Okay, next we dive into RSA. RSA was invented in 1977 by Ron Rivest, Eddie Shamir, and Leonard Adleman. It needs large keys, minimum 2048 bits, to be considered secure, at least for today's computer. It can only handle small data. Maximum data size is key size minus padding, which for 2K key like this one will give you approximately 245 bytes. So it's suitable for key exchange. There is a newer asymmetric crypto, is the elliptic curve. It's faster than RSA. It uses smaller keys. A 256-bit key is has equivalent security of a 3,000-bit RSA, and it comes with a hybrid mode. Okay, now I'll go into some details on how we have implemented support for these, and we start by having two traits. One trait is for symmetric, another trait is for asymmetric. Looking at symmetric first. The symmetric trait needs some parameters and a cipher. These must be implemented by the class extending the trait. The trait provides an encrypt method. As you see, it's Java security code all over, but this is what we're trying to hide. And it also has a decrypt method. Let's look at how you can use this trait when implementing AIS. So we start by having an object extending symmetric. We define the parameters with some good parameters. And then we need to implement the new cipher. And this is pretty good. These things you need to check to follow what's needed for today. Okay, now let's look how we can encode or encrypt the plain text. So we get in plain text. We use a passphrase here. So the encrypt method is using a passphrase. So the user has to give the passphrase. And for passphrases, we need to do key stretching to get it a little bit more secure. And for that, we need a salt. So we create a salt. We stretch the key, the passphrase into a key. AIS also needs an initial vector, an IV. So we create that one. And then we do the encryption here. So we get the ciphertext. And then we put the plain text, the manifest. We also put the salt, the IV, and the ciphertext into the ciphertext class. So, any questions so far? Okay, in code, you will use it like this. You give a passphrase and you just go encrypted, and you get all that done. So you can see that all the complexity is hidden in the implementation. And decrypting, you do it opposite. Since we wrote the encrypt method, we know that you will get 4 bytes out, or 4 arrays out. So you split it out, you do the key stretching the same as we did before, we decrypt, and then we return the decrypted and the manifest. Using it in code, well, it's important here that we use the same passphrase, because it's a symmetric crypto, and then we get back that. The asymmetric trait is very similar to the symmetric, but in addition, it adds the encrypt and decrypt methods for the plain text. We don't have to do that. And like the symmetric trait, we need a cipher. And the encrypt method is simple. We use a public key, and we take the plain text bytes and that key, and then we do encrypted. This is from the asymmetric trait, and this is how that is implemented. So this one calls this one, and if we want to implement our RSA, we start by having an object. We set it up in a good way. This is the cipher, and we provide a key pair function for good measure to make it easy to use. And this is all we need to define if we use the asymmetric trait. And in code, we do this. We get a new key pair. We make the public key a given to be able to use encrypt. Decryption, it's not that hard either. You take the private, you need a private key. We split up the ciphertext, we decrypt it, and we return it. The decrypt method is this array private key running the cipher that we defined before and returning the bytes. Using it in code, we only need to make the private key available. You can do decrypt. And remember that RSA can only encrypt limited data for 2K key, 245 bytes. So we can use hybrid to fix that. And that's a little bit more involved. We create this AIS hybrid thingy, where we have the encrypt method using public key, and we have the decrypt method using the private key. And the implementation is like this. Generate an symmetric key. In this case, we don't need key stretching because we are generating 256 random bits for a key. And then we need to generate the IV. We encrypt using this. And finally, we use RSA to encrypt the symmetric keys bytes. And we put everything in here, the plain text, the IV, the encrypted key, and the encrypted text. Decrypt, well, use the split function. Use the split function to get out the parts, decrypt the key, create the key from the bytes, get the IV to get the spec, do the decrypt from the trait, and then we get back the text and we return this. Elliptic curve. This is going to be simple because we have the same thing we do in object, extends asymmetric. We do a lot of, the cipher things need to be set up correctly. This is kind of boring. And we have a new key pair which you can implement. But that's all we need to do, the new cipher and the new key pair. And then we can use it like this. Get the key pair, make the given key, the public key given, we can do encrypt, decrypt, just make the private key given, and we can decrypt. Now, to summarize, if you're going to use Cryptic, the simplest way, you start by importing this. This will give you the RSA AIS hybrid crypto. And then you need a public key, and you can do this. And decrypt, you need a private key, and you can decrypt. And that's all I had to say about Cryptic library. Have any questions so far? Okay. If you want to learn more about cryptography, Stanford has a really good course called Cryptography 1, and it explains all the things much better than I have. Okay, and this is the GitHub for all the code and this presentation.
It's very long.
I would like to follow up on the first question because your answer was that all the developer needs to do is to provide a function that not sure what the function was to decrypt the thing or to resolve the key.
It was encrypt and decrypt.
Encrypt and decrypt function. Okay.
Two functions. One
Yeah.
from plain text to ciphertext, and the other one from ciphertext to the trial of plain text.
Okay. My question is that sometimes you don't have the keys available in the process. Sometimes the keys live in some repository, in which case this function would need to go to that repository, fetch the key, and only then decrypt. And if the API mandates to use only a function, then it needs to be a blocking function, right? And not something, a function that blocks. I mean, not a function that returns a future or cuts I/O, but synchronous, right? Synchronous call. So have you thought about addressing this limitation maybe?
No, that's correct. So we need to put that into the list to support futures in the function. Good point. Thank you.
Thank you.
This was now all about encrypting all the data with the same keys, I guess. Do you have some insights or how you would do then key management to encrypt the data for each entity on its own?
Well, looking at our example with Caesar with a key ID, that's something that you can do if you associate an ID, because the ID of the key is not secret, and you can store that into the data. So that's one way of doing it. Otherwise, we don't specifically address key management, because that's that's another topic. We use keys if the function use keys.
Yeah, but exactly, you could say that making this mapping from key ID to the real key, then you could always keep track inside the data that, okay, I'm using this key ID here. That's not, like, we know that it's this user's key, right? But where you get that key, how you get hold of that's another problem, of course. You need to solve that as well.
Yeah, thank you for the talk. My question is, why bouncy castle?
It's a well-known crypto crypto provider. It's used in the Java world. But as I show you, you can implement anything. This was in the elliptic curve here. When we did the implementation. Let's see. Sorry. For this, since all you need to do is you need to provide a cipher and you need to be able to generate a key pair. Changing this to some other implementation, that's not hard. This uses somewhere here. It will become bouncy castle. So you just make your own if you want to have other.
Maybe a question about the API you showed at the very beginning when you were showing like some lazy mapping, lazy collect. Yeah. About serialization of this return value. Like if it's lazy, how do you serialize it back? Because you get the same type encrypted. But if you get an encrypted from the DB and then you want to re-serialize it into a DB,
okay, so
if it's lazy, how do you do it?
So if I should go back, I guess. Or should it be like this? Okay, let's see here. So you actually don't get an encrypted value back. You get something called Cryptic, which is let me go there. You get back something called, it was the operations, right? Somewhere here. Let me see. Sorry about this. Where's the operations?
Very beginning.
Yeah, here, right? Somewhere here. Let's go here. Okay, so hi, operations, right? So what you get back, so once you've done upper here, you won't get encrypted back. You get a base trait called Cryptic. And then in this case, it will be a subclass of that called mapped, which holds the mapping function you use, right?
But it will be convenient to have a serialize that will like
the
key re-encrypt it and re-serialize it.
So if you look at the sample I had here, so here it says it's, no, in the email, it's even earlier, I guess. Yeah, here in the person class here. So this is encrypted, so you can't store it if you mapped it here, because then you will have to change this to be cryptic, or maybe mapped if you're really sure you always map it. Otherwise, Cryptic would be able to store stuff here, if the cryptic trait, I mean. But if it's encrypted, it needs to be fully resolved down to something that has no staged things left, right?
And we do have a method called run that also takes the decrypt function. So that's, you can do decrypted and then it will do run. That will run all the stages, and then you come into an encrypted, and from that you can access the cipher bytes.
Yeah, but we chose here for simplicity just to, like this is like the one you'll see most, right? Because you don't want to keep half stage stuff.
It's encrypted here on the left. It should be cryptic.
Yeah, you're right. That should be Cryptic. So there you see. Good catch. Thank you.
Okay, let's end off this talk. Thanks very much for the talk.
Yes, thank you.
Thank you.